Awesome. All right. So yeah, as Osias hands some stuff out, I'm just going to kind of introduce him. Osias, his project was prototype for refrigerator efficiency, and his mentor was David Denkenberger. So yeah, we're looking forward to hear from you.
Hello, hello. Hopefully everybody on Zoom can hear me. But as Jeff said, my name is Osias Salem. And for this past summer, I had the privilege of working with Dr. Denkenberger on his prototype for refrigerator efficiency project. Now, the essence of this project was really to develop a heat exchanger that's cheaper to manufacture than traditional microchannel heat exchangers. And traditional microchannel heat exchangers are generally made out of metal, and the complex of such heat exchangers is generally very complex. So as you can see on the image on the right-hand side of this slide, it's a lot of just repetitive geometry. And so our goal was sort of to simplify this design in such a way that it's more easier to manufacture, and two, to simplify it in such a way that it can be assembled out of lithium or low density polyurethane, which is the plastic, the black plastic bags. So yeah. Also, the end goal of this project really was to replace the current heat exchanger in a standard mini fridge and conduct effectiveness testing for comparison. Right now, we're a little bit behind in schedule, but we're hoping to still be able to accomplish that by September 30. This slide is out of order. I'll probably go back to that. For specific project goals, many of the responsibilities I was in charge of was just improving upon the existing polymer heat exchanger design. And I say improve upon the existing design because this project has been such an ongoing one for many, many years now. And really, I just represent like a little 10-week sliver in this entire process. And so I hope I was able to contribute some, but really, a lot of what I was in charge of was just learning how to assemble it in such a way that it wouldn't break after a few hours of use. Once we successfully assembled these heat exchangers, we were able to gather effectiveness data by taking thermocouples and taking temperature readings of the inlets and the outlets of the heat exchanger. Right now, we're in the process of designing a chassis to withstand the operating pressures because the refrigerator that we're planning to install our heat exchanger in has a very high operating pressure with a very low driving pressure. And I'll be continuing on with the team until maybe the end of September to write a research paper to publish our findings. Now, why are we doing this in the first place, And really, it's because heat exchangers have such a wide variety of use cases. They're used everywhere. They're used in internal combustion engines. They're used in air conditioning units. And one of the cases that we looked into was using them to utilize the waste heat from diesel generators in remote Alaskan communities. And we really feel that if we're able to harness that waste heat from the diesel generators, we can repurpose that for absorption chillers, which is an effective energy solution for Alaska and has implications beyond just Alaska. For the methodology of this, I said before that really we got stuck on the assembly process of this just because it's such a fragile piece of equipment. And not only is it a fragile, it's just a plastic bag that we're welding together. We're using sort of a makeshift laser welder in this process. And the makeshift laser welder is really just a modified 3D printer that previous students before me really fixed up to where the X and Y axis of it are exactly the same as to any 3D printer, but instead of extruding filament, it actually just outputs a laser. And so this next slide is how you'll be able to see where this laser welder is really just welding the two pieces of plastic together to get the specific designs that previous students have designed. But as you can see, an entire huge chunk of my frustrations and my efforts this summer was just dealing with inconsistent welds and the frequently leaking, broken heat exchanger layers. And this was something that I struggled with for super, super long. And it felt like it had been like 5 weeks already. And we weren't able to assemble anything that would hold up long enough for us to gather data on. And yeah, it was a big frustration, but I'll go in a little bit later as to how it really forced me to have a growth mindset, which is something that Jeff mentioned on orientation day. Also, personally, I feel like my largest contribution to this project really was just learning how to optimize the use of our laser welder, because it's such a makeshift piece of equipment. It's not really commercial grade by any means. So I think learning to ways to clean it and learning ways to keep an eye on it, because it would be really frustrating when it takes about an hour for each of these black layers to print, and then you'd put it together, and that process would take an hour with all of the hose clamps, and you'd have to tighten it all by hand because it's just such a fragile process. And then at the end of that 2 or 3 hour long process, however long it took you to assemble it, it would just leak anyways. And you can imagine how frustrating that was, but it was a healthy learning experience, I believe. Now, the expansion process for testing was also tedious in and of itself, because if you've ever filled up a water bottle, or if you've ever filled up a piece of glass straight from the faucet, you'll notice that there's tiny little micro bubbles that sort of generate on the inner surfaces of the water bottle or the cup of glass. And really, if we're pushing in just straight up faucet water into our heat exchanger, you're effectively just creating a layer of air, which really greatly affects the effectiveness of our heat exchanger, because air has such a lower thermal conductiveness compared to water. So we had to use a special water, deoxygenated water, which is just a fancy way of saying water that's been boiled off. And we had to flow this water through our heat exchanger for about 2 hours before we could take any testing data. And because of those 2 hours, we'd frequently experience weld leaks and bursts just because of the pressures that this heat exchanger had to withstand. And as you can see in this photo, you'll see exactly how expanded it is when it's actually operating. So it had to be able to withstand all of that. Eventually, though, we were able to gather some data finally, and we're happy to report that our effectiveness data was suggesting that our heat exchangers could operate near 80% effectiveness, which is a significant increase as to what the heat exchanger was in the current mini fridge that we were planning to replace. The current heat exchanger in our mini fridge was about 50%. So in terms of the lessons that I've learned, though, because there were so many frustrations and because there were so many broken parts that just kept happening, I really learned that there's so much to consider when you're designing a working component, that taking something from computer design and bringing it out into the real world, there's just so many variables that are difficult to predict when you're building something in real life. And there are just so many different little things that could interrupt your process of bringing something that's designed on SolidWorks into your hands. And I personally had little experience with that in the past, so I'm glad that I had some exposure to that during this summer. And also, if I were to give myself advice, 10 weeks ago, I'd say keeping a legitimate list of the improvements you've made to a design would be a good idea, just because oftentimes I would make a small change, and in making that small change, you'd birth a new problem, and trying to fix that problem interrupts the other small change. And it was just a very lengthy experience, I suppose. And for concluding remarks, I already said I felt like my greatest contribution was just learning to use the laser welder. And I think even before I was on this project, there was some struggles with the team utilizing the laser welder for a few months before. So I'm glad that that was something that I was able to contribute, and that was something that that was one of my successes. Moving on, I feel like I've iterated how frustrating it was, but I really did enjoy learning about all of these new pieces of technology. Prior to this, I really had little experience with 3D printers, and I really had little experience with laser welders at all. So being exposed to that and really understanding how the code interacts with the machinery, I thought was very fascinating. And then lastly, as Jeff mentioned on orientation day, the growth mindset was just such a necessity during this entire project, because specifically with ones like this one where it was almost entirely hands-on, and specifically because we're trying to make a pressurized vessel, it was just incredibly difficult. And being exposed to that many failures and being able to view it as, lessons learned was just a valuable experience for me. And I'm thankful to Acep for giving me this opportunity to really develop that growth mindset this summer. And I'm thankful to all of the interns I got to meet. And I'm thankful for Dr. Denkenberger for really being patient in this process because of how slow the progress seemed. And it seemed like an entire struggle this summer, but I feel like it was a necessary struggle. And luckily for me, I just so happened to be the student that was chosen for that. So that's all that I have for my presentation, and we can move on to questions now. Speaker. Sorry, could you say that again? So personally, my experience with this, the question was, has there been studies on the effectiveness of heat exchangers over time and the effects of using polymer instead of regular metals? So the idea behind the polymer heat exchanger was, to bring the costs down. And we know that the thermal conductivity of LDPE, low density polyurethane, is a lot lower than using aluminum because, well, metal just conducts heat very well. But the idea was just to manufacture it in such a way that the plastic was so thin that it would still be able to conduct heat very well. And in terms of longevity with these heat exchangers, we really don't have as much experience with it, just because, at most, the longest that one of these has lasted during a testing procedure was maybe like 3 days. So oftentimes they would the structural integrity of the heat exchanger would break before we would notice a significant drop in effectiveness. Okay, so actually this graph is an NTU. Oh, the question was, what was the NTU of the heat exchanger that we were trying to replace in the refrigerator? Personally, I don't actually know because that testing was done previous to my arrival to this team, but I do know that NTU is a function of the surface area of the heat exchanger against the flow rates. And there's a coefficient C_min, and it's calculated through specific heat capacity and mass flow rate. And really the reason that NTU is changing on the x-axis of this is because we used varying flow rates. And that's why the x-axis is able to vary. The surface area of our heat exchanger stayed the same because we only had one design, but the flow rates that we were using to calculate effectiveness was varying. Cameron. So the effectiveness is a measurement of the total heat transferred to the system compared to one flow rate's change in temperature. So we can take the change in temperature from the intake of the hot flow and compare that to the change in temperature over the entire system, if that makes sense. Oh, and the question was, well, how is effectiveness and how is it measured? Maury. So the question was if low density polyurethane, if I know why that material was selected for the project. And I've read in Dr. Denkenberger's previous papers that making polymer heat exchangers is something that had been studied a little bit before. But in terms of just the application of using that specific polymer in our project, I believe it's just because it would be the simplest material to use our laser welding technique. Cole. The question was, how did we fix our leaks? And I mentioned a little bit in the presentation that the laser welder would often develop inconsistent welds. And I don't know if you saw the differences between one sheet of this layer and the next sheet of this layer, but in one of them, the welds are just very flat, whereas the next one, it almost looks damaged in a sense. So we had to mess with the output of the laser and the duration of the print time to sort of generate an idea and a procedure as to how long we should be using the laser welder for. And also, a lot of it did just come down to making sure we clean the glass every single time. And also, instead of using a spray adhesive to keep the plastics in place, we just started using tape instead, because we noticed that using spray adhesive on the platform really, it raised the elevation of the plastic pieces a little bit higher, and it brought it closer to the laser welder. Lindy. Yes, exactly. So that's also why I suppose that we wanted to use this material, was just because it was so accessible already, because low density polyurethane is really just those heavy duty plastic bag liners that are pretty frequent. Cool. So our testing procedure wanted us to use about a 50 degrees Celsius intake for the hot flow and near 0 degrees Celsius, so ice cold water as possible in the cold flow. The pressures we haven't been able to measure yet. How could we make the welds better? Well, it was a matter of expanding it in such a way that we did it carefully so that it would last longer during the testing procedure. But also, it was just a way of optimizing the way that we use the laser welder also. So really, the welds came down to how well the laser welder was operating. And very early on in the project, it felt like it was just sort of hit or miss or very random as to why we would get poor welds. But I think as I progressed throughout the project, I learned of ways to operate it in such a way that it would give me 100% reliable welds. So I believe the code said that it would go over the lines about 3 times. So the laser would actually pass through each little weld 3 times. But it also depends on how thick we wanted the welds to end up being. Sweet car. So the the question is, are the channels 3D printed? And really, the chassis is the only thing that was 3D printed, which was the gray housing. But also the channels are made from just making individual weld lines. And then when we push air or water through the heat exchanger, it creates and expands into the micro channels. Are there any more questions? Cool. Thank you for listening.